Okay, here
Yes.
today we'll start a new unit, that is Unit 5, Unbalanced three-phase systems. Three-phase systems. Okay, we already studied balanced three-phase system, star and delta networks in basic electrical engineering. Okay, there before starting this unbalanced three-phase systems, first we'll just look into what are the balanced three-phase systems. Okay, with this background, we'll start with unbalanced three-phase systems. Okay, everyone know this one? If in a balanced three-phase system, all the three system voltages are equal and separated from each other by how much degree? Yes?
120 degree.
Yes. In a balanced three-phase system, all the three system voltages are equal and separated from each other by 120 degree. So that I can say my currents also separated from 120 degree each. So I can write the equation like this. First one, three phases R, Y, B. Okay, first R as the reference phase. Tell me, EM sine omega t. Here ER is the reference phase. Now EY sequence is RYB. Okay, my ER is EM sine omega t. EM is, yes, tell me.
Sin omega t minus 120.
Minus 120 degree. Then EB is
Em sin omega t plus 120.
omega t. I can say minus 240 degree or plus 120 degree. Correct? Okay. These are the three voltages. Three voltages. If I am saying this is my balanced three-phase system, all three voltages are equal and separated each from 120 degree. If I am taking ER as my reference point, EM sin omega t, this is EY is displaced by my ER by 120 degree. Same for if ER is a reference point, EB minus 240 degree. Here my phase sequence is R, Y, B. Okay, now the three-phase load can be connected to a three-phase system in two ways. First of all, tell me what is balanced load? Balanced three-phase load. Balanced three-phase load. Yeah, tell me. Balanced three-phase load.
So in all three phases, the load value and type
Phases.
will be
Yeah. If I am going to say balanced three-phase load, all the three loads, that is impedances, are at the same nature and displaced by a 120 degree, as well as the magnitude will be same. So I can call those loads are balanced three-phase load. Okay, now I can connect this balanced three-phase load in two ways. What are those two?
Star and delta.
Yes. First one, I can connect this balanced three-phase load star and delta. Okay. Now I just draw one delta connected or star connected load here. I can connect a balanced three-phase load in star as well as delta. Okay, this R, this one is Y, this one is B. Okay, where this is my phase 1, Z phase 1, this is my phase 2, that is load phase 2, Z phase 2, this is my Z phase 3. What this point will called as? This point
Neutrals.
is a
N.
neutral point N. Okay, now if I'm going to connect one three-phase balanced supply, that is R, Y, B. This is my balanced three-phase supply. If I'm going to connect this one to my star connected load, okay, R to R, okay, Y to Y, then B to B. Okay, here this is my three-phase balancer supply. I'm going to connect this one to the balanced three-phase load, that is star load. Due to this supply, current in the lines, these are called lines, supply to load. The connection between supply and load terminal, I'm going to call it as a line. So due to that supply, the current will flow. Okay, this current is IR. Okay, then IY and IB. IY and IB. Okay, here the same current will flow in the phases. See here, the line current, this point to this point to this point, IR is flowing, and the phase 1, that is R to N, the same current is flowing. Okay, this is IR. Same here, IY is flowing in the line as well as the phase. Both are same. This is IY. Then IB. IB is flowing here, so here it will flow IB. Now we can conclude from seeing IR in the line as well as IR in the phase. I can say for star connected load, the line current and phase currents are equal. IL is equals to I phase. This is my balanced three-phase load as well as balanced three-phase supply. It's a star connected where I can conclude IL equals to I phase. Then the voltage across the phase. How we are going to write? Phi Rn here. Phi Rn. Voltage across the phase. It's call it as phase voltage. You guys know this one, just I am brushing up this one. V, then V, Yn, voltage across this phase, Y phase, and voltage across B phase, V, Bn. Generally, while writing the equation, N we are not going to write, so VR, Vy, Vb are my phase voltages. The voltage across the phase, this is my phase where I connected my impedance. Voltage across the phase is VRN, VYN, VBN. These are the phase voltages. Okay, then voltage across the line will be my what? Voltage across the line, VRY. Then yes, VYB. Then VRB. Voltage between two lines or across the two lines, VRY, VYB, VRB. These are my line voltages. Here, the line voltages are not equal to phase voltages. That is in case of star connected load. Correct? Now, same I can connect in delta. So, here if I connect that one in delta, these are my three phases. Okay, this one is RYB, RYB is going to supply here R Y and B. Okay, now I can say Z phase 1, Z phase 2, Z. Here also voltage across the line VRY, VYB and VRB. These are the line voltages. Then voltage across the phases VBR. Okay, voltage across phase VRY, then VYB. From this diagram, we can conclude that in a star connected load, my line voltages are equals to phase voltages, that in delta connected load. But what about the currents? If current IR is flowing here, IY is flowing here, IB is flowing here. Okay, when this IR reach to this point, is going to divide into two lines, right? So I can simply say IR is not equal to whatever the current flowing through the phases. It means line currents are not equal to phase currents in delta connected load. Then how I am going to denote those line currents? R to Y, IRY, Y to B, IYB, B to R, IBR. Okay, just keep in mind in star connected again and again, just this is a simple one, but you have to remember this one. If you understand, no need to remember also how this current in the line as well as in the phase in a star connected is equal. And here voltage across the lines and across the phases are equal in delta connected. Okay, everyone understood this? Say yes.
Yes, sir.
Yeah. Yes. Now tell me the equation for power. We know we derived a equation for power in basic electrical engineering. Okay, where we found out that the power is the same for both the star or delta connected load. So now tell me the power, that is active power P is equals to, see, first of all tell me how many types of power will be there. Just
Three, sir.
remember the power triangle. 3. Apparent power.
Reactive power and active power.
Yes. Apparent, reactive, active. Okay. I am going to denote this active power as P. Now tell me the expression for P. We are dealing with 3 phase. So root 3 VL IL cos pi. Correct? Active power P is equals to root 3 VLIL cos pi. What is the unit of this?
Watt.
Watts. Now coming to apparent power. Yes. Root 3 VL IL. What is the unit for apparent power?
Volt.
Volt ampere. That is VA. Then reactive power, that is Q. Root 3 VLIL
Sin pi.
sin pi. What is the unit of this reactive power?
Volt ampere reactive. VAR.
Yes, that is VAR, volt ampere reactive. Okay. If you know this, now we'll proceed with the unbalanced systems. Okay. Now here first in unbalanced three-phase system, we know what to mean by balanced load. Now unbalanced load. Unbalanced load. Before that, once again I am going to repeat the definition for balanced load. The balanced load is which we're going to call when all the impedances are of the same nature and displaced by an angle of 120 degree, and all of them are equal in magnitude. Now please anyone try to define unbalanced load.
They are loads which are not of the same nature. They are not
Yes.
displaced by the same angle, or
Yes.
they are not same in magnitude.
Yes. Unbalanced load, the definition for unbalanced load is that in which the impedances in a three phase having different values. That means they are not of the same nature and they are not displaced by an angle of 120 degree, and the magnitude also be different for unbalanced load. Where I'll give one small example for this.
Should all the three conditions be satisfied, or even if any one is there,
If
with unbalanced load?
yes, if any one, in the sense, see what I said. First point is same nature.
Yeah.
Second
Okay.
point is
That's by angle.
same magnitude. Okay, third point is angle. Okay, if any one of these will affect, means we are going to call that one as unbalanced load. Or the current will be different in all the three phases. Okay, balanced load in the sense what? The current flowing in all the three phases. If I'm going to connect the balanced three phase supply to the balanced star load or delta load, the voltage across the load as well as current flowing in each phase will be the same. Okay, then we are going to calculate the power in any one of the phase. Then multiply the power with the number. If I am this, I'm going to calculate the power in any one of the phase. Then I'm going to multiply the number of phases. Current will be the same, voltage across that will be the same. Current will be the see. You understood that point, right? Arjun?
Yes, sir, I understood.
Yeah. Now, see, example we take this one. This is star connected load. R. Okay. B. This is Y. Okay. R. Y. Now, Z phase 1, 3. All this one as an unbalanced load. First, the magnitude has to be different. Correct? I mean to call it as this one as 20, this one as ohms. Then the angle they displace from each other. This one is 60°. Then this one is minus 80°. This one is 0°. So now I can call this one as unbalanced load. So here, if these are three currents, IR, IY, IB. Okay, all these IR, IY, IB all not equal due to the difference in their magnitude as well as their phase displacement. As well as I can draw a unbalanced load, delta load, where I can see R, Y, B. R, Y, B. Okay, here 79 angle of 10°. Okay, 8 an angle of 10, 10, 20. Then this 15 angle of 30°. These are in Z impedance ohm. So here also IR, IY, IB are not equal because they are different in their phase differences with the other phases. So I can tell IR, IY, IB in the above diagrams are not equal. Okay. Now, once the impedances or once the connected load is unbalanced, then get the different current flowing through their phases. Here we can see These all are different currents. The current flowing in this phase is depend on this impedance, that is 15 and angle of 60°, and same for all the three phases. Here for delta connected load, current flowing here I Ry is also depend on this 8 angle of 20°, load dependent currents, so that we will get the different phase currents for each phases. In that case, what we need to do? We need to calculate the power in every single phase. Then we need to add them up. But in case of balanced load, we are going to calculate the power in only one phase. Then we are going to multiply that power with number of phases we have. Okay, now I can write the equation for this. Just remember this circuit. So depend upon this only, I'm going to write some equations. Now here, I know, otherwise I'll draw a circuit for the equation references. I'll consider one star connected load, star connected unbalanced load. Okay, this is R, this is Y, this is B, R, B, Y it come, RYB. This is unbalanced. Okay, Z1, Z2, Z3, or I can call Z phase 1, Z phase 2, or Z phase 3. Current flowing in the line is IR, IY, IB. Then the voltage is VRY, VYB, then VBR. Okay, this is my neutral point. And if I'm going to connect neutral to my supply neutral, that neutral, this is a supply neutral, this is RYBR supply, this neutral is the supply neutral, this neutral is the load neutral. If I'm going to connect this star connected neutral point to my supply neutral, then there is no voltage difference between them. It means the voltage between the neutral point of my star connected load as well as the neutral point of my supply connected load is 0. If I am not going to connect this neutral to my supply neutral, then just the voltage between the neutral of this connected load as well as my supply node. Now here in this diagram I connected, so the neutral voltage will be 0. Okay, now I can write IR or neutral current IN is equals to IR plus IY plus IB. Okay, then VRN, that is here, VRN is nothing but, tell me what is VRN?
IR into Z1.
No, here VRN, what is VRN?
R and neutral point.
Phase voltage, correct, right? The voltage across the phases, phase voltage, VRN, VYN, VBN, these are the phase voltages. Okay, now I can say, I'll write the equation for phase voltages as VRN, or I can simply say VR or I can simply say phi phases. Please unmute yourself, Aditi. Yeah, phi phase. So I can write, see here, we know phi Rn, phi Yn, phi Bn are the phase voltages phi Y, phi B, phi phase, phi phase, phi phase. Okay, if R is my reference point, my sequence is R, Y, B. Phi phase as angle of 0 volts, phi phase an angle of minus 120 degree volts, Vb for Vb an angle of minus 240 degree or plus 120 degree volts. Now if Z1, Z2, Z3, Z1, Z2, Z3, if I am going to write the equation for these impedances, yeah, tell me. Z1, this Z1, yes, see here current IR, see this IY, IY, see this IB. Now tell me the equation for Z1, simple Ohm's law. Z1 equals to, this Z1 equals to,
VRN by IR.
yes, phi Rn, sorry, phi Rn divided by this one, IR. Okay, we know phi Rn is here, phi phase an angle of 0 degree divided by IR. Okay, now I am going to say these are displaced by the different phase angles, not other than 120 degree, not than 120 degrees. So I am going to call this one as, this angle is pi 1, this angle is pi 2, this one as pi 3. Okay, now I can write Z1 angle of pi 1 is equals to phi phase an angle of 0 divided by IR. Then IR equals to phi phase angle of 0 degree divided by Z1 and angle of pi. So simply I can write IR equals to phi phase divided by Z1 angle of minus, if this pi plus pi will go to the numerator from denominator, it will become as minus pi ampere. Correct? IR equals to phi phase by Z1 with the angle of pi 1, that is pi 1. Understood? If you say yes, I will go further. Understood?
Yes, sir.
Yeah. Now tell me the same for IY and IB. IY and IB. IY is equals to, see this, IR is V phase divided by Z1 angle of minus pi 1. Now Iy. That is nothing but phi yn divided by Z2. Yes, Z2. Here we know Vyn is phi phase angle of minus 20 degree. Z2 is Z2 angle of pi 2. Now tell me. Phi phase divided by Z2 is an angle of
minus of
minus 120
pi
degree
2.
minus pi 2. Yes,
Yeah.
correct, Arjun. Okay, now at least please kindly tell me for IB.
Sir,
AB equals to, yeah,
PBN divided by Z3 and
VBN divided by Z3, then that is
V
VBN.
plus angle is 120 degree plus 120.
Yes,
Z3 phi 3.
Z3 pi 3. Okay. Now V phase divided by
Z3
Z3.
120 minus phi 3.
120 minus pi 3. Yes. These are the three equations we are going to get if my load is unbalanced. That is, they are going to displaced with pi 1, pi 2, pi 3. Okay, if they are going to displaced with pi 1, pi 1, pi 1 for all the three phases, then I simply get the current in all the three phases will be equal. Here currents are different. Okay, now 42. Okay, now in next class with this basics we'll um, see some problems. Okay, everyone understood this?
Yes, sir. Yes,
Yes.
sir.
Yes, sir.
Yes.